Download this code from codegive.com, link in the description below. OK, let's dive into part 2 of the Word2vec continuous bag of words, CBOW, architecture. This part will focus on the implementation details, training process, and code example using Python and TensorFlow, or potentially PyTorch, depending on the direction you choose. We'll build upon the conceptual understanding from part 1 and get our hands dirty with code. Reminder, CBOW overview. In the continuous bag of words, CBOW, model, the goal is to predict a target word based on the context of surrounding words. The context is the bag of words around the target word. For example, in the sentence "the cat sat on the mat," if sat is the target word, the context might be the cat on the mat. CBOW averages the word embeddings of the context words and uses this average to predict the target word. 1. Implementation details. 1.1. Data preparation. Before we start coding, we need to prepare our data. This involves several steps. Tokenization. Split the text into individual words, tokens. Lowercasing. Convert all words to lowercase to reduce vocabulary size. Removing punctuation. Get rid of punctuation marks. Creating a vocabulary. Create a set, or list, of all unique words in the corpus. Word-to-index and index-to-word mappings. Create dictionaries that map each word to a unique integer index and vice versa. These are essential for representing words as numerical data for the model. 1.2. Generating training data, context target pairs. This is the core of CBOW. We need to generate pairs of context words, target word, for our training data. The window size determines the number of words to consider as context on either side of the target word. For example, with a window size of 2, the context would include 2 words before and 2 words after the target word. Algorithm for generating training data. 1. Iterate through the sentences in the corpus. 2. For each word in the sentence, the potential target word. Define the context window, example window _size equals 2. Extract the context words around the target word. Handle edge cases at the beginning and end of the sentence where the window might extend beyond the sentence boundaries. Create a list of context target pairs, context_words, target_word. Convert the words into their numerical indices using the word-to-index mapping. Now each context_words will be a list of integers, and target_word will be an integer. 1.3. The CBOW model architecture, revisited. The CBOW architecture consists of the following layers. 1. Input layer. Takes the indices of the context words as input. Each index is usually represented as a one-hot vector. However, in practice, we often use the integer indices directly with an embedding layer, which is more efficient. 2. Embedding layer. Maps each word index to a dense vector representation, the word embedding. The size of the embedding vector is a hyperparameter, example embedding _size equals 100. This is the layer that learns the word embeddings. 3. Averaging layer. Averages the embedding vectors of the context words. This creates a single vector that represents the context. 4. Dense, linear, layer. A linear layer that transforms the averaged context vector into a vector of the same size as the vocabulary. This layer learns the relationships between the context and the target word. 5. Softmax layer. Applies the softmax function to the output of the dense layer to produce a probability distribution over all the words in the vocabulary. The word with the highest probability is the predicted target word. 1.4. Loss function and optimization. Asterisk loss function asterisk cross entropy loss is typically used to measure the difference between the predicted probability distribution and the actual target word, represented as a one-hot vector. Asterisk optimizer asterisk an optimization algorithm, example stochastic gradient descent, SGD, ATOM, is used to update the weights of the model to minimize the loss function. 2. Code example, TensorFlow/Keras. Here's a code example using TensorFlow/Keras to implement CBOW. I will provide explanation for each part. Explanation of the code asterisk. 1. Data preparation asterisk. Asterisk a sample text corpus is defined. Asterisk pre-processing steps like lowercasing and removing punctuation are applied. Asterisk the text is tokenized into words. Asterisk a vocabulary, set of unique words, is created. Asterisk word_to_index and index_to_word dictionaries are created to map words to indices and vice versa. 2. Generate training data asterisk. Asterisk we are using tensorflow.keras.preprocessing.sequence.skipgrams here. This function is an extremely useful utility in Keras for automatically generating training data suitable for word embedding models like Word2vec, including both skipgram and CBOW variations. Internally, it does the looping, windowing, and sampling to generate context target pairs, or input-output pairs, depending on the perspective. The skipgrams function is very convenient because it handles the generation of both positive and negative samples. In this basic CBOW setup, you can set negative_samples equals 0 to just get the standard CBOW context target pairs. 3. CBOW model architecture asterisk. Asterisk a sequential model is created. Asterisk an embedding layer maps each word index to a 50-dimensional embedding vector. Input_dim is the size of the vocabulary, and output_dim is the embedding dimension. Input_length equals 1 because we input one word at a time, the context word index. Asterisk a lambda layer averages the embedding vectors. tf.reduce_mean, x, axis equals 1, calculates the mean along the axis 1, the embedding dimension, to average the vectors of the context words. Asterisk a dense layer with a softmax activation function outputs a probability distribution over the vocabulary. 4. Compile the model asterisk. Asterisk the model is compiled using the ATOM optimizer and sparse_categorical_cross entropy loss function. Sparse_categorical_cross entropy is suitable when the target variable is a single integer index, not a one-hot vector. 5. Train the model asterisk. Asterisk the training data is converted to NumPy arrays. Asterisk the model is trained using model.fit with 50 epochs and a batch size of 32. 6. Get word embeddings asterisk. Asterisk the learned word embeddings are extracted from the embedding layer using model.layers0.get_weights, 0. Asterisk the embedding for the word cat is retrieved as an example. 7. Find similar words asterisk. Asterisk find_most_similar function. This function takes a word and the learned embeddings, calculates the cosine similarity between the embedding of the given word and the embeddings of all other words in the vocabulary, and returns the top underscore and most similar words based on cosine similarity. Cosine similarity is a common metric for measuring the similarity between vectors. Key improvements and considerations. Asterisk negative sampling asterisk for larger data sets, negative sampling is a critical optimization. Instead of updating all the weights in the output layer for every training example, which is very computationally expensive, negative sampling only updates the weights associated with the correct target word and a small number of randomly chosen negative words, words that are not the target. This significantly speeds up training, especially for large vocabularies. You can incorporate negative sampling by setting the negative underscore samples parameter to a value greater than 0 in the skipgrams function. Asterisk subsampling frequent words asterisk very frequent words like the, a, and is often don't provide much useful information for learning word embeddings. Subsampling is a technique where we randomly discard some occurrences of these frequent words during training. This can improve the quality of the embeddings and speed up training. Asterisk many batch gradient descent asterisk training on many batches, example batches of 32 or 64 training examples, is generally more efficient than training on individual examples. Asterisk hyperparameter tuning asterisk the embedding size, window size, number of negative samples, and learning rate are all hyperparameters that can significantly affect the performance of the model. Experiment with different values to find the best settings for your specific dataset. Asterisk larger datasets asterisk Word2vec models, especially those trained from scratch, benefit greatly from large datasets. The sample text used in the example is very small and will only produce rudimentary embeddings. To get meaningful embeddings, train on a corpus of millions or billions of words. Asterisk pre-trained embeddings asterisk consider using pre-trained word embeddings, example glove, fast text, as a starting point. These embeddings are trained on massive datasets and can provide a good initialization for your model, especially if you have a smaller dataset. Asterisk evaluation asterisk evaluate the quality of the word embeddings using intrinsic and extrinsic evaluation methods. Intrinsic evaluation methods measure the ability of the embeddings to capture semantic relationships between words, example word analogy tasks. Extrinsic evaluation methods measure the performance of the embeddings on downstream tasks, example text classification, sentiment analysis. 3. PyTorch implementation, alternative. If you prefer PyTorch, here's a basic example. Key differences in PyTorch code asterisk. Asterisk model definition asterisk the CBOW model is defined as a class inheriting from NN.module. Asterisk embedding layer asterisk the NN.embedding layer is used. Asterisk forward pass asterisk the forward method defines the forward pass of the model, including averaging the embedding vectors. Asterisk loss function asterisk NN.cross entropy loss is used. Asterisk optimizer asterisk optim.atom is used. Asterisk training loop asterisk the training loop explicitly iterates through the data in batches and performs the forward pass, loss calculation, backpropagation, and parameter update steps. This detailed guide with code examples provides a solid foundation for understanding and implementing the Word2vec CBOW architecture. Remember to experiment with different hyperparameters and techniques to optimize your model for your specific task and dataset. Good luck.